Relative frequency. A six-sided dice was thrown repeatedly. After every 100 throws, a cumulative number of sixes thrown was recorded. Complete the table below, which gives us a summary of the results obtained. Cumulative means ongoing. So, for instance, what that means is, in the first 100 throws, there were 8 sixes. After 200 throws, there were 28 sixes. So that meant between 100 and 200, in the 100 throws in there would have been 20 sixes. All right, to complete the table for relative frequency, relative frequency is like the probability of how many times it's occurred. So for the first one, you're doing 8 divided by 100. For the second one, it's 28 divided by 200. The third one would be 60 divided by 300. The fourth one is 72 divided by 400. And the fifth one is 80 divided by 500. Okay, when you're looking at doing the divide here, okay, like for this one, 60 divided by 300. All right, you can cross the 1 naught off, and then you're asking yourself how many 30s go into 6. All right, you can cancel that down. 6 goes into 6 once, and 6 goes into 35 times. So that is 1 out of 5, or as a fraction then, how many 5s into 1? 5 into 1 doesn't go, note down, carry the 1. 5 into 10 goes 2, nothing left over. So that is the same as 0.2 or 0.20. The next one, 80 divided by 500. That is going to be the same. Okay, I can cross the 1 0 off for this next one. I'm asking myself how many 50s go into 8.00. How many 50s in 8 doesn't go? Note down, carry the 8. How many 50s in 80? 1 50 is 50, 30 left over. How many 50s in 300? 6, so it's 0.16. So when you plot this on the relative frequency graph, okay, you'll be looking at the highest number is 0.20. So I would probably on the side is 0.10, and then going up in the next 10 squares is 0.20. So each one represents 0.01. So 0.01, 0.2, 0.3, 0.4, so on, up to 0.1. Right, so I'm plotting for 100 throws, the relative frequency was 0.08. So it's across 100, up 8 squares, and where 100 meets 8 squares is where you put your cross. Across 200, up 0.14, 0.10, 0.11, 0.12, 0.13, 0.14. Across 300, up 0.20. Across 400, up 0.18. Across 500, up 0.16. So 0.11, 2, 3, 4, 5, 0.16. From the table, which value gives the best estimate? The best estimate is always the one after the most times. So the one with the most accurate is 0.16, because the most accurate results occur after the experiment has been repeated the most times. Okay, the next one. Do I think that is a fair dice? Because a dice, the probability of getting a number on a dice is 1 out of 6, and 1 divided by 6 is, how many 6 in 1 doesn't go, note down, carry the 1. How many 6s in 10? 1 6 is 6, 4 left over. How many 6s in 40? 6 6s are 36, 4 left over. So in terms of a dice, it's 0.16 or 0.17 to 2 decimal places. So yes, I would say it's very fair, as our answer was 0.16 in the table. Is very close to the real one from the real theory of 0.17. So I would say yes, it's very fair. Next question. A factory uses a machine to produce electrical sockets. The manager carries out a survey to investigate the probability of the machine producing a defective socket. The relative frequency of defective sockets was calculated after 1,000, 2,000, 300, 3,000, 4,000, 5,000. They plotted on. So what they're saying is after 1,000, the probability of the relative frequency is there. So like this would be 0.02 and that's 0.04. So 1, 2, 3, 4, 5. In the middle would be 0.03, and then going up it'd be 0.032, 34, 36, 38, and 4. So how many of the first 3,000 sockets were detective? So I go into defective. I'm going from 3,000, I'm going up to the point, and I'm going across. It's right in the middle of 0.04 and 0.6. So it's going to be 0.05 would be the relative frequency. Because it's out to 3,000 goes, it's times 3,000. And then, because it's a calculator question, because it's unit 2, you just type in 0.05 times 3,000, and it comes up as 150. Write down the best estimate for the probability that one socket selected at random will be defective. Give a reason for your choice. The most accurate is the more times you've done the experiment. So it's here. So this one is 0.04, 0.042, 0.044, 0.046, 0.048. And the reason being the more accurate probability occurs after the experiment has been repeated many times, the most times. So the 0.048, the more accurate probability occurs after the experiment has been repeated the most times.